We're going to talk about trusses briefly. This was something we covered in detail, at least on one of the quizzes. In the final, there are some truss problems, but not too many, and they're not very difficult. So let's make an example problem here. Trusses are these, triangular, boxy structures like you see bridges being made out of all the time, etc. Okay, we have some load here. Let's call this 100 pounds. We have some load here. Call this 500 pounds. And yeah, that's plenty. Now, first thing we want to know is what are the reaction forces here. Call this RB. Call this RA. And then we need dimensions. So let's say all of these are equilateral triangles of 10 feet. So each thing here is 10 feet, etc. We know RA plus RB equals 600. That's the total forces here. And we know that the sum of the moments about A equals to 0. Always the case, still is the case. So, find the moments about A. We have 100 pounds times 10 feet. And that's a moment in the negative direction, according to the right-hand rule. Minus 10 times 100. Minus, see, we have 500 pounds here. If we look at the line of action, we draw this little dotted line, see where it goes. So this is going to be 5 feet, this will be 5 feet, that'll be 10 feet. So that's 25 feet away, the line of action for this 500 pound force. So 25 times 500. Then we have the positive moment from RB, so that'll be 30 times RB equals to 0. We'll pull out our calculator and find RB. We have 1,000 plus 25 times 500. 13,500 divided by 30, 450. And then we know that RA is going to be 600 pounds minus 450, so we have RA equals 150 pounds. Now, in the quizzes, we had to find out what the internal forces were in some of these members. This is still possible. You cut the beam mathematically apart like this, and you know that this whole section of matter and this blob here has to be in its own personal static equilibrium. So there are forces at the boundaries from the beam, here, 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 and you apply all the same equations and you can find out these forces if you must. Now for the final, we don't actually have to do this. All we need to do is to know how to recognize this truss, look at the loads on it, if they're applied here, or here, or here, and find the reaction forces correctly. So that's all that's on the final exam. One caveat. Probably spelled that wrong. On the final, there is a problem that has a vertical load on the beam, like this. The arrow is drawn as up. It's a lie. It should be downward. One of the problems in the final exam, you will see an up arrow like this for some load on a truss. that load should actually be down for you to get the correct answer. That's trusses. Now go on to stress and strain. Stress versus strain. So what we need to know about the stress versus strain diagram. We have stress up here, strain down here. And the question is, if we have this little, bar of wire or steel or aluminum or copper, whatever it happens to be, we put it in some machine and we just pull it harder and harder and harder until it fails. And we plot the stress, which is, how hard we pull, divided by the area of what we're pulling on, and the strain, which is basically how many inches this thing gets pulled versus how many inches it started off as. And that gives us the stress-strain diagram for a given material. You will typically get a diagram that looks something like this. So some steel, you pull on it, it actually starts to stretch at some point, and at some point it just can't take anymore and it breaks. So let's look at some critical portions of this graph. There's a linear region in here where this is perfectly straight. You go up some amount in strain, you pull it a little bit, you get some amount of stress. You do it twice as much, you get twice as much of the other. Perfectly linear. At some point, this will leave the curve. We call this the proportional limit, or the elastic limit. If we go much higher than that, we start to get some appreciable what's called plastic deformation. That means once you let go of this thing, it's not going to be the same shape it was before. So if you let go of this thing, you get rid of all the stress, it will collapse back down at the same slope, but you'll end up not quite back at zero. If you end up at 0.2% strain, this is called the yield point, and this is how you define when something is yielded. Basically, like if you see this in a building, it's broken. This is not correct. So you have your origin, you start stressing the material, you stress it, you stress it. If you get to the proportional limit, you're kind of at the point of no return. If you let off under this, you'll come right back to zero. The material is unharmed effectively. If you get up to the yield point, however, and you let go, it will drop back down and you'll have some permanent strain show up in the material. Like if you pull on this bar, it's going to be longer bar than it was before you pulled on it. And that means it's yielded. For a building, that's usually going to mean broken and incorrect. So know what these points are. This is the elastic regime or the proportional regime. The slope here is the Young's modulus, E, that we've been using in this course. And once you go up past that on this curve, you get to the yield point. And that's when, if you let go, there would be some permanent deformation in the bar. If you just keep pulling and pulling and pulling and you pull the crap out of this thing, you'll eventually get up here to where it breaks. This breaking is called the ultimate strength. This is not something that you should ever design to, because up here it is absolutely no more. So this is the very most that something can take. You'll often see like a steel cable or something like that that has some ultimate strength of 100 kip or something like that. But you should typically not use it more than 20 kip. It would be like a reasonable safety margin to stay under for a cable. For the final exam, You mostly just need to know this curve and the names of these points and what they mean. And that's it for that micro video.